Welcome. Today's lecture we're going to start in on Unit 1.2. So this is part A of that. There'll be a part for each section in the textbook for Chapter 2. So today we're going to be talking about displacement, but I'd like to talk about the bigger picture first. This is a discussion of kinematics. So kinematics is an important discipline in physics. Kinematics is the study of motion of an object without considering its causes. Kinematics. Kinesiology, the study of motion. Study of motion of an object without considering its causes. If you want to consider its causes, then the motion along with its causes is a field called dynamics, which we'll start covering, I believe, in Chapter 4 or 5. So, kinematics. We're just going to be looking at objects and how they move for now, not why they move. The objects and how they move, we're going to assume the objects are small. We're going to assume that they are rigid and that it's a baseball flying, not a blob of jello or water or anything like that, and that they're not spinning. We're going to be talking about rotational motion later on this semester, but for now we're going to just look at objects pretending they're not spinning. So baseball flying through the air, we're going to assume it's not spinning. Now baseballs, of course, are designed to not have a smooth flight when they're not spinning. It's called a knuckleball. But we're going to pretend that doesn't happen. No air resistance. We're not going to consider air resistance until later. We're not going to consider friction until later. We're just talking about the motion of objects. So assume everything's in a vacuum, everything's frictionless. You're on a thin surface of ice with a thin layer of oil on it, as slippery as you can make it when we're studying this object. So kinematics, specifically, we're going to focus on one-dimensional kinematics. One-dimensional, or 1D, is important. We're going to be looking at, right now, in this chapter, motion along a single line, a single axis. We're not going to be considering two-dimensional motion until later. We're going to start very simple and work our way to more complex ideas later on this semester. So for right now, we're just going to be looking at one-dimensional kinematics. Now, that one dimension can be horizontal, a block sliding across a table, or a car driving on a road, or you walking on a sidewalk, or it can be vertical in that a ball falls directly down after you drop it. Now, once we master one-dimensional motion, we'll talk about the idea behind vectors. In fact, we're going to do that in a little bit. Then we'll expand into two-dimensional motion, a baseball flying through the air, or a cannon firing through the ground, or a tennis ball after it's hit off of a racket. But first we have to master the one-dimensional ideas before we master two-dimensional motion. Now, this lecture has a lot of new physics concepts that you'll be introduced to, not new concepts in general. I'll be using terminology like speed and velocity, distance and displacement, acceleration, and defining those for you today. However, just to let you know, there are specific physics definitions for these terms. So, before we start talking about motion, we have to talk about, well, what is motion, right? What is movement? Movement is when an object is in one position and then it changes that position to go somewhere else. Okay, now, so motion has to do with position. Well, how do you define position? Well, to do that, we have to create what's called a coordinate system. So we're going to be looking at these Cartesian coordinate systems. Our Cartesian coordinate system you probably used in previous math classes, especially with graphing. It's a simple x, y, z coordinate system, where the x-axis is often depicted as a horizontal line going left and right. The y-axis is often depicted as a vertical line at 90-degree right angle to the previous line, going up and down. And then the z-axis will be coming out of the board at the camera or going into the board away from the camera, which of course I can't draw very effectively on this board. Now, three-dimensional motion is very complex. We're not going to be really addressing that in this class. We're going to be sticking probably mostly to two-dimensional motion, but we have to set up our coordinate system. Typically, the vertical coordinate will be given the terminology y, as in plus y, and minus x and plus x for the horizontal coordinate. So when an object moves horizontally, it's moving in the x direction. When it moves vertically, it's moving in the y direction. Now, I did say that we're going to be looking at just one-dimensional motion for now. That one-dimensional motion we're going to be looking at, we will pick one of these coordinate axes and just stick with it. We'll start with the x, and then we'll talk about free fall later on with y. Note how I have these set up. Horizontal motion is x with the positive direction going to the right and the negative direction going to the left. Direction is important. If an object moves to the right on my coordinate system, it has positive motion. If it moves to the left, it has negative motion. Same with the y-axis. Up is positive, downward motion is negative. That's very important when you set up a coordinate system to set it up in such a way to be consistent. Now, every problem I'm going to set up, I'm going to use this coordinate system unless I specify otherwise during that problem. Now, I could make the right negative x and the left positive x. I could make up negative y or down positive y. Then that's fine as long as you're consistent in your problem. But this is the most standard way to set it up, and there's no reason to go against the textbook, and most textbooks do it this way, so we'll stick with this. So assume this coordinate system unless otherwise informed. So we're going to be dealing with one-dimensional motion, so let's erase this and move to just a one-dimensional axis. And then define position. Position is just where is the object located. Well, it's easy in colloquial language. It's 10 feet. Well, 10 feet from what? 10 feet from me, 10 feet from you, 10 feet from the door. If you're measuring the height of an object, where is the object located? If you're dropping a ball off of a roof, do you have the ball height to be 0 at that point? Or is the ball measured from the ground below, or measured from your feet? Where do you put the position of an object? That's where coordinate systems come in. Define a coordinate system. Define where the 0 point is. Is the 0 point you? Is the 0 point the start of the motion? Is the 0 point the ground? And stick with that definition as we move on. So if I have an object, like a person, standing here, I can say that person is at some position x. Now, if there are multiple people, I can say this person is at x1, and this slightly shorter person is x2. Subscripts, the little numbers below the letter, help us keep track of which position we're talking about, which person we're talking about, and so on. Different books use different subscripts. Just note that this is a handy way of just keeping sense of all the positions you might be given. So where is the object located? Now, let's imagine, so position's fairly straightforward. The next term we have to worry about is displacement. For displacement, it's just a change in position. So we're looking at, in this case, where does the object move? If the object is moving, that's what a moving object does. It doesn't stay in the same location. It moves its position. It changes its position, it moves. So if a person starts off at that position X and then moves, same person now is at some other position. Well, what do we call that position? Well, if it occurred at a later time, we'll say that the position started off at some initial position, x naught. The little 0 at the end means naught. Some people say x0, but it's often referred to in physics as naught. So x naught is the initial position, and then to some final position, x sub f. Now, different books use different subscripts. Some use x sub f for final position and x sub I for initial position. Some just use x alone for final position and x naught for initial position. Your book kind of uses both, a hybrid of the two. X final for the final position, x naught for the initial position, and we're going to be consistent with your textbook. So we'll start with this. So displacement is a change in position. It's given by the variable, so displacement. It's given by the variable we'll use is delta x. The little triangle there is the Greek letter delta, capital Greek letter delta. This delta refers to change in. So whenever you see a delta anywhere in your mind, just say change in. So delta x means change in x. And that's a displacement, how x changes. Delta x for an equation, change in position x, is x final minus x initial. Highlight that because it's an important equation for displacement. So here we have an equation giving a displacement. Notice the order. Final position minus initial position, not the other way around. Well, what if your initial position is larger than your final position? What if I start off over here? I define that area over here as x equals 0. I'm now at x equals 2 meters. Well, if my final position is x is 2 meters, my initial position is 0, my displacement is positive, I've moved in the positive x direction, and I did, right? Moving from here to here, I've moved in the positive x direction. If I start here at x equals 2 meters, I still have that as my 0 point in the coordinate system over there. If I start at 2 meters and I move to 0 meters, position 0 here, 0 minus 2 is negative 2. My displacement is negative. It means I've moved in the negative direction. So displacement has two pieces to it. There's a number, which gives the magnitude of the displacement. How big of a move did I do? And then the sign of that number tells you in what direction. So displacement is a vector, and we'll talk about vectors in the next video. So the sign of the displacement is important. You must keep those. It depends on how you set up your coordinate system. Final minus initial, always. Never the other way around. Now, displacement is a very specific physics term, and we'll be using that term quite a bit, of course. Oh, focus is going a little odd. I'll fix that in the next video. So the displacement is a very important topic. In physics, there are two. In colloquial language, you might confuse it with distance. Where the displacement of an object, delta x, and the distance of an object, the distance traveled by that object, or the distance of that object, might seem similar. But in physics, they're actually distinct. Distance is the magnitude of the displacement. By magnitude, another way of saying that, it's the absolute value. I can spell. The absolute value of the displacement. Remember, displacement is positive for a positive displacement, is negative for displacement in a negative direction. So the sign is important when you talk about displacement. For distance, the sign is not important. In fact, there is no sign. It has to be positive. So moving from here to there or there to here is the same distance. They're identical because the absolute, if it's 2 meters, positive 2 in one direction, negative 2 in the other, the absolute value of positive 2 is 2. The absolute value of negative 2 is 2. They're the same. Now that is also distinct from the distance traveled, which is the total length of path traveled between two positions. What do you mean by that? Well, let's imagine I'm going from here to there. If I go in a straight line, the distance would be 2 meters. It's probably not quite 2 meters, but let's pretend that it is. Distance traveled, what if I did this? Up and down and closer. The focus is probably going crazy, but up and down. And then I wander back here, and then wander over here, and then stop. The distance I moved is still 2 meters. The distance traveled is actually significantly more. Think of distance traveled like the odometer in your vehicle. So let's put all these things together and talk about the distinction between displacement, distance, and distance traveled. Let's imagine you have a garage where you park your car before you go to work, overnight in your garage. So you have your garage at some position, your initial position. You drive from your garage, you take your car out, and you drive to work, which is your final destination. Well, the displacement of your vehicle between those 2 points is just equal to x final minus x initial, or x naught, sorry. Again, different books do it different ways. I may make that mistake because that's the way the textbook I usually use does it. But this is our displacement. Now, we've defined this to be a positive displacement because the car is moving to the right, the positive x direction. If I have the car going in the opposite direction, if I start there and I move back, it would be a negative displacement. The distance traveled is the absolute value of either of those. The distance cannot be negative. Displacement can and often is half the time. Right? Displacement to the right is a positive displacement. Displacement to the left is a negative displacement. Distance has no sign. Distance traveled is distinct from the two. And here's an example to get that in your head. You start off parked in your garage in the morning. You drive all the way to work, and you come all the way home and park back exactly in the same spot in your garage. The displacement between leaving for work and coming home from work is 0. Because your initial position was the garage, and your final position is your garage. So your initial position in that example is equal to your final position. You park in the same spot. So when you plug these two things into this equation, since x final is equal to x initial, there is no displacement. Think about it this way, right? Your spouse or your children or boyfriend, girlfriend, roommate, whatever, wakes up, sees the car in the garage in the morning, and before they go to bed, they see the car in the garage at night. They don't know you took it to work. To them, the car hasn't moved, right? No displacement. The distance traveled in that example is also, the distance is also 0, because the distance is just the absolute value of the displacement. The displacement is 0, the distance, the absolute value of 0, is 0. Now, the distance traveled is not 0, because you've driven to work some miles away, say 10 miles away, you've driven back, which is another 10 miles, your odometer has ticked away 20 miles, that's the distance traveled. It is important to understand the distinction between displacement and distance traveled. We will be using displacement in this physics course.